Welcome to BuildBytesDaily. All right, today we're pulling back the curtain on a piece of tech that's, well, it's pretty much a secret weapon. It's one of the most important performance innovations out there, and it silently powers the super fast, dynamic web you use every single day. Yep, we're talking about just-in-time compilation.
So, have you ever stopped and wondered about this? How did JavaScript, a language that, let's be honest, used to get a lot of flack for being slow, suddenly become this absolute powerhouse? I mean, it's running some of the most demanding apps on the planet. Think Figma, Google Docs, even intense browser-based games. Well, the answer is this really clever technique that completely changed the game.
All right, so here's the game plan for today. We're going to start with why JavaScript even had a speed problem in the first place. Then we'll look at the two classic ways to run code, interpreters versus compilers. After that, we'll see how JIT swoops in as the best of both. We'll dive into how it actually works, touch on the hidden costs, and wrap up with just how huge its impact has been. Let's get into it.
So let's rewind a bit. Back in the early days of the web, JavaScript had a pretty simple gig, right? It was there to do little things, like make sure you filled out a form correctly, or create a cool little pop-up. And for that, the way it was designed worked just fine. It was purely interpreted, which just means a program read the code line by line by line and ran it. But then our ambitions for the web got way bigger. And that slow, one-line-at-a-time approach, it started to become a major roadblock.
Okay, so to really get why the solution is so brilliant, we have to understand the two classic ways people have been running code for decades. You've got your interpreters on one side, and your compilers on the other. They're like two totally different schools of thought.
Let's use an analogy here because it makes it super clear. Think of an interpreter, like a live translator at a conference. They hear a sentence, they immediately translate it and speak it out loud. It's super flexible, happens right there on the spot, but there's always that slight delay, that translation overhead for every single sentence. Now, an ahead-of-time compiler, or AOT compiler, is totally different. It's more like a professional who translates an entire novel. They take the whole book, spend a bunch of time translating it perfectly, and then publish the finished version. The upfront work takes a while, but once it's done, anyone can read that translated book at native speed. The catch, of course, is that the translation is now locked in for that one specific language.
So you see the dilemma, right? On one hand, you've got flexibility. On the other, you've got pure, raw speed. For the longest time in computing, you kind of had to pick one. But what if you could have both? What if there was a way to get the best of both worlds? Well, this is exactly where just-in-time compilation makes its grand entrance.
And the key is right there in the name, just in time. What it does is translate your code into super fast machine code at runtime. I mean, while the program is actually running. So it's not doing everything up front like a traditional compiler, and it's not stuck translating line by line forever like a simple interpreter. It's this incredibly smart, dynamic hybrid that gives you the raw speed of compiled code with all the flexibility of interpretation.
And you know, this isn't some brand new idea that just popped up. Not at all. The basic concepts were actually floating around way back in the 1960s with Lisp. Then in the 80s, a language called Smalltalk really started pioneering things like compiling code on demand. But the moment it really hit the big time was in the 90s when Java made JIT a household name for developers. And it's still evolving. Just look at PHP 8.0 adding a JIT compiler. The point is, this is a seriously battle-tested and mature piece of technology.
Okay, so we've covered the why. Now for the really cool part, the how. How in the world does a JavaScript engine like the V8 engine inside Chrome just magically make your code faster while it's running? Let's look under the hood, because this process is fascinating.
So here's how it plays out. First, your code just starts running normally with a basic interpreter. But, and this is the clever part, while that's happening, a profiler is watching everything from the sidelines. It's like a coach with a clipboard, taking notes, counting how many times every loop runs and every function gets called. It's looking for the bits of code that are doing all the heavy lifting. And these busy sections, they have a name, hotspots. As soon as the engine identifies a hotspot, it's like, okay, you're up. It sends that piece of code over to the JIT compiler, which turns it into highly optimized native machine code. Then, the next time that piece of code needs to run, the engine swaps out the slow interpreted version for the new, lightning-fast compiled one. Simple as that.
And that term, hotspot, is so important. It's basically the 80-20 rule in action. You know the idea that 80% of the work gets done by 20% of the code? A JIT compiler knows this. So instead of wasting time compiling everything, it focuses all its energy on optimizing just those few critical hotspots. That's how it gets such huge performance gains. It's all about working smarter, not harder.
And here's the real magic, the secret sauce, adaptive optimization.
See, a normal ahead-of-time compiler has to guess what kind of computer the code will run on. It has to be generic. But a JIT compiler, it has home field advantage. It's running on your machine right now. It can see exactly what kind of CPU you have and use special instructions tailored just for it. It can even see how you're using the program in that exact moment and make optimizations on the fly that a static compiler could only dream of. It's incredible.
Now, this all sounds a little too good to be true, right? And, well, in the world of engineering, there's no such thing as a free lunch. JIT is amazing, but it does come with a couple of trade-offs, a few hidden costs that we need to talk about to get the full story.
The biggest one you might actually feel is something called warm-up time. Take a look at this chart. When you first launch a complex web app, it starts out running in that slower interpreted mode. All that profiling and compiling has to happen in the background, and that takes up a bit of time and CPU power. So you get this initial period where performance is just okay. But then, once the JIT has found the hotspots and compiled them, boom, you see that massive jump in performance. This whole process is exactly why a big application like Google Docs might feel just a little bit sluggish for the first couple of seconds before it hits its stride.
Then there's the security side of things. To do its job, the JIT needs to be able to write new machine code into memory and then turn around and execute that same memory. Now, from a security perspective, having memory that is both writable and executable at the same time is a bit of a red flag. It can open the door to some clever exploits, like something called JIT spring. Of course, the engineers who build these engines are all over this. They use some really smart protections. One of the main ones is a simple but powerful rule. A page of memory can be writable or it can be executable, but it can never be both at the same time. This constant switching of permissions makes it much harder for attackers to exploit the process.
So now that we're through the nitty-gritty, let's just zoom out for a second and really appreciate what this technology has done. Because the impact of JIT compilation goes way beyond just JavaScript, it has fundamentally shaped the modern web.
And really, this quote from Wikipedia just nails it. It's a combination of the two traditional approaches, which combines some advantages and drawbacks of both. It's not some magic bullet that solves every problem, but it's an incredibly powerful and pragmatic compromise. It takes the best parts of two opposite philosophies and creates something way more powerful.
And this right here is the bottom line. I want you to think about the tools you probably use every single day. Things like Figma, Google Docs, all those amazing 3D games you can play right in your browser. These things are not just websites. They're complex, powerful applications. And that massive leap, the very thing that allowed us to build applications this powerful that run at near native speed right inside a browser, that was unlocked by JIT compilation, plain and simple.
So, let's wrap this all up. What are the key things to remember? First, JIT is that smart hybrid, mixing interpretation and compilation. Second, its whole strategy revolves around finding and optimizing those hotspots. Third, it makes a trade, a little bit of warm-up delay in exchange for huge long-term speed. And finally, and most importantly, it's the key that unlocked the door to the high-performance web we all know and love today.
It's honestly hard to overstate how much JIT changed the game. But it does leave us with a really interesting question to think about. If JIT was such a massive leap forward, what's the next big leap? We're already seeing things like WebAssembly push the envelope even further. So I'll leave you with this. What do you think is the next frontier for runtime performance?
Hey, if you enjoyed geeking out on this stuff with us and found this whole explainer helpful, it would mean a ton if you could hit that like button and subscribe to BuildBytesDaily. We really love diving deep into the tech that builds our world. Thanks so much for watching, and I'll catch you in the next one.